Okay. So what we have done in the last classes, whatever we try to do in the last classes, we try to find out the bending moment and the shear forces for each and every portion, like whatever you have studied in the theory of structures one. So I have taken here, if you see, I have taken the first portion. Okay. This is the portion which is 2.439. So the distance is 2.439. We have a UDL going from the bottom to the top. Okay. And it is similar to a cantilever beam. So the bending moment for the cantilever is WL square over 2, while the shear force is WL. Your W is your pressure, your load is your pressure, which is 428.045 multiplied by the length, which is 2.439, and you can calculate. Okay, let me finish from here, Amira, and then you can ask. Okay. And once again, keep the questions, unless they are really urgent, keep them to the end of the session. Okay. So once again, we have 1,444 as a shear force, and we have 1,273 as a bending moment diagram. Now, if you can see, I have plotted the 1,044. I have plotted the 1,273. Okay, so 1,444, 1,273. We have finished from it. And then what I have done for the second portion, I have taken this particular portion. So I'm trying to finish from the edges first. So I took the left edge, and then I took the right edge. The right edge is having a distance of 2.411 till the face of the column. So I have taken 2.411 to the face of the column. Once again, we have V using the same equation. WL, your W is the pressure only. It's direct substitution with the equation. So we have got 1,032 and 1,244.1. So I have plotted 1,032. Since I'm starting from the other direction, in shear force, you need to flip. You need to flip the direction of drawing. Okay. So 1,032, and then we have 204.1 here. Okay. Now after we have finished from the edges, whatever is remaining for us is going to be the middle portion. Okay. Now for me to calculate the middle portion, bending moment, because we have finished from this bending moment. Okay, let me just try to do. So we have got this bending moment, and we have got this bending moment. We have finished from here, since these are the face of the support. Now, if you remember, we normally require the bending moment at the support, and we require the bending moment at the span. So we have finished from the support. Remaining is the span. Now, for me to calculate this particular value, I need to refer back to the shear force diagram, using the concept of minimum shear is going to be the maximum bending moment. Okay. Or zero shear force is going to give you the maximum bending moment. Okay, so what we have seen here, we have drawn the bending moment, the shear forces first. We have calculated 771 and then 727 using these equations. So for the first scenario, I have taken 2.439. There is a loading here, which is 1,890. Okay, and this is 0.175. I use the equations. Okay, directly. The equation of bending moment for the UDL is WL square over 2. The equation for bending moments for a point load, because we have point load and a UDL here, it's going to be WL only. Okay. You need to know the cantilever equation if it's a point load for shear force and bending moment, and then once again if it's a UDL, what's the bending moment and shear force equations. Okay. So if you remember, we said I think I have given you the equations last class. The bending moment is WL square over 2 in case of the UDL, and then in case of a point load it's WL. In case of shear force, the UDL it's WL, and in case of point load is W only. Okay, so we have calculated, okay, 3, and we have got the value to be 771 with a negative sign, so 771. And then later on I took the other portion. Okay, I took the other portion, okay, which is going to be this particular part now, okay, this particular part. And we have drawn once again the free body diagram, and according to the free body diagram, I have calculated shear and bending moment using the equations once again. Now, whether you are using the equation or whether you are using the area of the shear, both of them, they will give you the same answer. The only thing that you need to make sure that your values or the dimensions or the lengths you have taken are correct. Okay. Now, if you remember yesterday, one of the things, just not to let you confuse, okay, yesterday when we have tried to prove the shear force diagram, especially the shear force diagram, assuming that we are having a point load here, okay. If you remember, whatever we have done, we said this is the side of the column, this is the side of the column. Whatever we have tried to do, we tried to calculate the shear force here. And then whatever we have done, we just calculated once again at the center here. And then we reduce the value of the point load. Do you remember this that we have done last class? Do you remember this, whatever we have done last class? Okay. Now, if you see whatever I have done, in this particular example, using the other method or using the other concept, where I have done it in this way. You'll see I have used this is. You will see that I have used it in this way. Okay. So whatever I have done, instead of drawing the point load line, I have drawn it in this way. Now, do you think this is correct? Which method of the two is correct? Now both of them are going to have the same value at this point. If you take this point, and if you take this point, both of them, they'll give you the same answer. If you go and see whatever we have done today, you will see that this is 700. This is 771. Okay. Now, if you go back to your calculation, how much we have got it for the calculation? How much we have got it for the calculation last class? Do you remember how much we have taken last class? Or how much we have got that value? Have we got the same values using both equations? Now you can see that we have got it 771 as well. Okay. Now, which of the methods? Okay, which of the methods is correct? Okay, which of the methods is correct, or do you think that both of them are okay? Both are correct. can go. Okay, so we'll not spend a lot of time. We'll not spend a lot of time. Now, in this particular theory, in this particular theory, which is theory number one, you are assuming that the column is acting at the center point only. Okay, and this is only for the simplification of the bending moment diagram. Now, when it comes to reality, the column is not only located at the center of the column. I mean, the loading will not be located at the center of the column. You will see that the loading is actually distributed along the column. Do you agree? Okay. Once again, both methods are used. One method is the simplified method where we are using the point load. The most accurate method is method number two, in which we have taken the column as it is in reality, where it's acting as a, I mean, the loading is distributed among the column. Both of the methods are used. Both of the methods will give you almost the same results. You can see here, if we refer to one of the reference books, this is one of the strongest books in RC design, reinforced concrete design by Mosley. You can see Mosley has taken it to be straight. He has taken the center of the column. Okay, and we have other references where they are using the accurate method, where you can see, for example, I have tried using a software. This is one of the few software which will draw for you the bending moment diagram for a combined foundation. You can see how the loading is acting in the column region. It's not acting to be a point load. It's rather than point load, it's becoming as a inclined line. Okay, so both methods are fine. I just wanted to highlight both methods for you. So if you have seen any book referring to the first method, then it's fine. If you are saying the second method, then it's fine. Are we clear? 90%, or let's say 95% of the cases or references, they are using the simplified one, which is case number one. Okay, software accurate thing, they are using method number two. Are we fine? Okay, so now we have got the shear forces all over. Okay, we have got 771 using the same methodology here, 771, and then we have used 1110 approximately. Okay, now if you can see, 726. So now we have 771.1, 727. This is the shear force diagram, which I have illustrated here as well. So we have two triangles, 771, and then we have 727. Okay, and we need to find the value of x in order for me to calculate the bending moment at this particular point. So how to find the bending moment? I mean, how to find the x value? We can use a similar triangle method, or you can use directly. The pressure. We know that the force here is 771, okay, and we know the pressure is how much. Basic concept says for you, if we want to shift from a UDL to a point load, we multiply by a distance. If you want to do the opposite way around, 771 is in kilonewton, 428.045 is in kilonewton per meter. So this is my UDL. This is my point load now. I want to get the distance. So you just divide them to get the distance. Okay. So 771.1 divided by 428, that's my pressure. It is giving me 1.801. It means the distance from the face till the point of zero shear force is 1.80, and we need to calculate the bending moment at that location. So whatever I have done, I have just drawn this part. Okay, I have taken this part where it's 1.801. So 2.439, which is the side here, and then we have 0.35, and then we have 1.801, which we calculated now. And then we have pressure going up, we have point load going down. Once again, we use the equation of bending moment we use the cantilever equations to find the bending moment. So we have got it at 774.41 kilonewton meter. Now, if you see here, a lot of confusion will be happening here. Now, the negative value, is it happening for the point load, or is it happening to the pressure? Now, which one is having the positive value? You can see from the equation, the pressure is having the positive value, the point load is having the negative value. Okay, so it means that the value, since it's positive, it means that it's dominated by the pressure. It's not dominated by the point load. It's dominated by the pressure, means it's going to go to the direction of the pressure. Now, if we return back and see, in this scenario, when we have drawn the bending moment, it's only dominated by the pressure, not by the point load, and the bending moment went up. In the other scenario, once again, we calculated the bending moment, it's only affected by the pressure, and it's going up. So it means that the pressure diagram will cause my bending moment to go up. And since here we are having the value to be 774 in positive sign, it means that your bending moment will not go down, but it will stay at the top. Okay, so what do we have in this case, which is a very rare case for a combined foundation, is that we are having a full top bending moment, and the reinforcement is only going to be in one direction. So once again, regular combined foundation, the regular combined foundation will be happening, or will have a bending moment in this way. Okay. Once again, sign convention can go and change from one reference to another reference. But what do we have? We have span moment, and then we have support moment. And normally they will be in different directions. That's why normally what do we have? We have a bottom reinforcement for the span. So we'll take this value of M, and then this is going to be the bottom reinforcement, which is, let's say, M positive. And then we are going to take the M negative, which is from the support. And then according to this M negative, we are going to supply one reinforcement here as well. Okay. So what do we have in case of a regular combined foundation? We have reinforcement at the top, we have the reinforcement at the bottom. Okay. Now, when it comes to isolated, if you remember the example of isolated, your isolated is having bending moment diagram or bending moment envelope in one direction. It means that we have only one direction of the reinforcement, which is at the bottom, since the cracking will be happening at the bottom. Okay. Now, whatever is happening with the combined foundation in this scenario that we have solved is the same as the case of isolated foundation, where all the bending moment diagram went only up and nothing went down. Okay, and then we are going to have the reinforcement at the bottom as well. Okay, although that we are using different sign convention, But once again, the sign convention will go from one person to another person differently. So whatever sign convention you want to use, you can use it as long as it does not contradict with your values, it does not show problems, then it shouldn't be a problem. Are we fine? Have you got what I said? Which part? Which part is Zahra? Once again, we said the regular bending moment that it goes up and then down. It goes down. This is the regular bending moment. In our scenario, because this particular edge is so long, it is long, they have not let my foundation bending moment diagram envelope go down. Once again, just to keep it simple. Now let's say that I have a steel bar here, and I have another steel bar here. Now, if we have the distance from the ground, to be, let's say, 30 centimeter, and I have a chain, Now, if you apply a loading, you would see that it's possible for this chain to go and touch the ground. Okay. I'm trying to refer here, touching the ground refers to going below the line of what you call the difference between positive and negative. Now, in the other scenario, if you have a steel element, the distance is 1 meter. You will see will the chain touches the ground or it will not touch. Which one you think that it will touch the ground? The first scenario, second scenario, 1 meter or 30 centimeters? 30 centimeters. And the concept of the height is referring to the same as the intensity of one. Meaning to say, if we are having an edge, okay, of 1 meter, my bending moment diagram will be certain value. And if I have an edge, or like your examples, for example, let's say 3 meter, you will see that the bending moment will get higher. Do you agree? Do you agree in this scenario? Do you agree that the 3 meter span will have a higher bending moment? According to the concept that you have studied, force bending moment is equal to force into this. So what happens in scenario number one? In scenario number one, we have a loading here, Okay. Now this is 1 meter. This is 1 meter, let's say. The second scenario, this is 1 meter. Let's say this is 3 meter now, and this is 3 meter. Now what happens? The bending moment here is smaller compared to this value. Do you agree? Okay. So for you, the chances of going below the line is higher at the top one, where it's lesser at the bottom one. Do you agree? Okay. So this is representing most of the cases of a combined foundation. We don't give higher dimensions. We don't give higher dimensions at the edges. Now, why we have done in our scenario, we have done because there was a constraint that the width is 2 meters. So I had to increase the length. Otherwise, I will not increase the length. I'll go and increase the width. Do you remember that there was a restraint of the width equal to 2 meters? Okay. Yeah, regarding the reinforcement, you mean? Regarding the reinforcement, or what exactly? Okay. So once again, I hope that I still remember whatever I have said. But anyhow, if you can see here, we draw the bending moment, and according to the bending moment, we go and do the reinforcement. Now, in this scenario, in scenario number one, since there is a top bending moment, we go and provide reinforcement. In the other side, the same thing. Since there is a top bending moment, we provide a reinforcement. Okay. Now, when we come to the bottom, we provide the reinforcement here as well. Okay. In reality, when it comes to the foundation, we extend the reinforcement from the beginning till the end. Okay. So we have the reinforcement in only one direction. Now we have the reinforcement in both directions due to the bending moment diagram. Now in the second scenario, we have, you can see that the bending moment is acting only in one direction. If the bending moment is acting only in one direction, it means that our reinforcement is going to be only in one direction. I hope it's clear now. Okay. So once again, there is another problem in your handout or your PowerPoint where you will be finding the case which is going to be the regular case. Okay. Now, if you see now how to find the reinforcement, later on. In this scenario, we are going to have moment of top, and then we have the moment of bottom. Or let's say top and bottom rather than saying negative and positive. Okay. So top and bottom. Okay. Now what will happen here? Okay, what's happening here? Okay, so what's happening here? We will be calculating one reinforcement for this M negative and one moment for this M positive. Now in this scenario, in scenario number two, all of the moment is only in one direction. The moment envelope is fully in one direction. It means that I don't need to go and calculate for 3 or for 2 values. I'll be calculating only for the maximum negative, because we are going to supply single reinforcement. Are we okay? Now, of course, this is only on the longer direction. We have the shorter direction as well. Are we fine? Okay. Now we talked about the longer direction. For the shorter direction, okay, I have tried to summarize, saying that the maximum long is 1,273 according to the problem. The maximum shear force at the face of the support is, or face of the column, is 1,044. If we return back to the drawings, you will see the maximum bending moment is here, and the maximum shear force is here. Okay, so 1,044 and 1,273. Okay. I have taken a picture of this particular calculation. I'll send it for you later in the Teams. Okay. Now, after we finish from the long direction, we need to go for the short direction. Okay, we need to go for the short direction. Now, how to draw the short direction? If you see, if I have drawn the foundation of this shape or in this shape, you will see that if I take the shorter direction, it will turn looking like an isolated foundation system. Do you agree? If I take it in the shorter direction, do you agree that now it's behaving like an isolated system? If we look at it from here, it looks like an isolated, only one column is there in the shorter direction. In the longer direction, we have two columns. Okay. Now, how to calculate the bending moment for the shorter direction? You need to use the same concept whatever you have used for the isolated foundation. We have got this particular dimension to calculate the face of the column, and then we use WL square over 2 to calculate the moment of the short. Now, the question says, why do we need to calculate the moment of the short? Because we said foundation is something similar to a slab. It will have two reinforcements. It will not have one reinforcement only. It means that we have reinforcement in the longer direction, and then we have the reinforcement in the shorter direction. The longer direction is going to be according to the moment that you have calculated for the longer, and then this one is going to be according to the moment calculated in the shorter. If you are having a top layer as well, then the same thing. So this is going to be moment for the longer. This is going to be the top now. This is going to be the bottom. This is going to be your shorter for the top. Okay, so we have completed by now. We have completed the bending moment and shear force calculation for a combined foundation. Okay. Now, calculation of the area of reinforcement is something which is easy, I believe. Calculating KZAS. So I'll not go and repeat it once again. We have done it in the slab. We have done it in isolated foundation, and I don't want to waste a lot of time in calculating it for a combined foundation. Is there anybody who is having a problem, does not know how to calculate for KZ and AS? Is there anybody who is having a, a problem in calculating KZ and AS? Okay, so the bigger problem is going to be in the matter of one-way shear and two-way shear, since we didn't discuss it. Okay, so one-way shear and two-way shear. Now I tried completely to finish one problem in terms of bending moment, calculation of reinforcements isolated, and then we have done the same for a combined foundation. Now what I'm going to do, I'm going to return back to the isolated foundation to work out the one-way shear and two-way shear, and then we'll return back to the combined foundation to check how to calculate for the one-way and two-way shear. Okay. And as I told you, this is a good reference, by the way. This is a good reference for you. Okay, this is a good reference for you if you want to go and and try certain problems, certain extra problems, you can try them out. Okay, this is one of the strongest books. I'll try to upload the book for you. Okay. Now, if we return back to one-way shear and two-way shear, if we return back to one-way shear and two-way shear, okay. Now, once again, for bending moment, we have clarified everything. Since we calculated bending moment, calculation of reinforcement will not be an issue. Okay. Once again, we are going to go and try to solve for one-way shear, whatever we have learned. Okay. So once again, I'm going to solve the previous problem in terms of shear force. Okay, in terms of shear force. So rather than solving it here, I'll go and solve it. I'm going to solve it here. Okay. So whatever data we have got previously, or whatever data we have solved previously, that we have got the d average. We have got d average, and if you remember, we said dx and dy, and I explained for you why we cannot use dx and dy. Okay. And we have the pressure to be 216.67. Okay, and then we said one-way shear will be acting where exactly? At a distance of how much? One-way shear. So if you remember, we said, okay, let me finish. Okay. We said for a one-way shear, it will happen, the shear force, okay, the shear force is going to happen after a distance of d. Okay, so this is d. Now, what does it mean? It means that if I have my column here, I have my foundation, we said the reinforcement will be, how the core of the column will be here. We said this is going to be your D. So when the pressure diagram, tries to, or the soil tries to push, you will see that in this area, it's hard to push, because this is the main area where the column is acting, the intensity or the loading of the column is acting. So it's easier for me, or it's easier, a cut will be happening in this region rather than happening in the center point where the loading of the column and the pressure of the soil is acting. Okay. Now, this portion, if it goes up, we need to calculate for it. Okay, we need to calculate this particular shear force. After the shear force, we need to calculate the shear stress, and we need to check whether the concrete foundation can take this particular shear stress or not. If it cannot take it, it means that this foundation is going to fail in shear. Okay? So we are trying to make sure that that particular portion is not going to be uplifted up. It will not be taken up by the pressure exerted by the foundation. Now the same thing goes for a two-way shear, or whatever we call it as a bunching shear. Okay. But rather than having it in one direction, we have it in both directions. Okay, and this distance in each side is 1.5 and 1.5 d. Okay. Once again, the first one is called one way, or we call it, some of the references are calling it to be beam shear. Okay. And then the second one is called two-way shear, or some of the references, or mainly we call it as bunching shear. Okay, mainly we call it as a bunching shear. Now, if we try to go and solve, according to the problems that we have. Okay, so we have, let's say that these are going to be for one way. I'm going to solve these for one-way shear now. Now, I need to keep a distance of d. Okay, I need to keep a distance of d, And then after that, the portion is going to be effective, okay, as whatever we have drawn, if you remember. This is my column. Okay. Once again, here is happening. You will see that this portion is going to be the portion which is uplifted. Now we need to know how much is this portion. So to calculate that particular stress, we need to calculate this particular dimension. Now, how to calculate the dimension? Let's call it to be, for example, x. X is going to equal to 3 meter. Okay. 3 meter minus the column. Okay. Okay. What was the column in this scenario? 400. The column is 400 square. So we are going to remove 0.4, dividing it by 2. So whatever I have got till now, okay, I have got this area. I have got this particular thing from the beginning till then. Okay, so 3 minus 0.4 divided by 2. Now I don't require this portion. So what we need to do? We need to go minus d. Okay. So now our solution is going to go as 1.3 meter minus d, and the d average that we are having it to be 0.48. So this is going to go so we are having it as 1.3 minus 0.48. So we are having this dimension to be 0.82 meter. Are we okay? Okay, very good. Very good. Okay. Now let's take the other scenario. Let's take the other scenario where we are taking now the other direction. So I'm keeping x. I'm keeping x here. I'm keeping a distance of d. And then after d, I'm going to check this dimension. So once again, what I need to do, let's call it as y. Okay. So once again, y is equal to 3 meter minus 0.4, since this dimension and this dimension are 0.4, since it's a square. So 0.4 divided by 2 minus once again d. Yeah. Yeah, but I need to explain, otherwise some of the students will not consider the other direction. Okay, so both directions you need to calculate. Now, since it's square, since the foundation is square and the column is square, the values are going to be the same. But if your foundation is rectangle and the column is square, your values are going to be different. If your column is rectangle, your foundation is square, then it's going to be different as well. Okay, so in both scenarios, we are having at 0.82 meter. So one of them, okay, any one of them is going to be fine since the values are the same. Now, what is the total force required for me to uplift this particular portion? What is the force required for me to take this particular portion up? How much force is required? Can you tell me what's the area of this portion? What's the area of this portion? The area? Can I say that the area? Can I say area effective? Area effective is equal to 0.84 into 3. Can I say like that? Okay, so this is going to give you 2.46 meters square. And can I say that the total force? Can I say that total force is equal to pressure multiplied by affected area or area affected? So can I say that this is going to be 216.67, which is in kilonewton per meter square, multiplied by a total area of 2.46. Okay. And since it's the same, to reduce place. Okay. So how much is the total force? The total force is 533.002 kilonewton. From here, Afaf, we just calculated. I said this length is how much, or this width is how much. We just calculated it to be 0.8.
Mr. But that's 0.84 and the previous was 0.82. Is it the same or?
No, this is now how much. Can you just check? Is it 0.82 or 0.84, the value? This one? This value is how much? Can you check this equation? This is 0.82. Okay, so here it's going to be 0.82. Can you check this value? Is it correct? Can you check the value of 2.46? Is it correct? Okay. Okay. So we have got it as 200. We have got it as 533.0082 kilonewton. Now this is a force or a stress? This is a force or a stress? $533.0082. Is it a force or a stress? Okay, of course it's a force because the unit is kilonewton. Okay, the unit is kilonewton. And then we have V. If you remember V, the equation of stress. What's the equation of stress? The equation of stress. Do you remember the equation of stress? Shear stress. What's the equation of shear stress? The equation of shear stress is equal to V divided by, is it by A or is it by BD small? Okay, so V small is equal to shear force divided by whatever we call it as shear area, or we call it as cut area. Let's call it as cut area. Let's call it as cut area. Okay. Now the shear force, we agree that it's 533.0082 multiplied by 10 to the power of 3, because normally we calculate the force, we normally calculate it in Newton per millimeter square. So I just converted from kilonewton to Newton. Now to keep it simple, normally to keep it simple, how many dimensions I need to cut? Okay, what are the things to be cut in order for me to remove this portion? What are the things to be considered if I want to remove this particular portion out of the foundation? If you assume that this is a cake now, okay, if you assume that this is a cake, I used to give the same example since you can easily imagine food. Okay, so if this is a cake and I want to remove that particular portion, how many things to be considered? Now, can I cut only for 1.5 meter? Can I cut only for 1.5 meter and this portion will be up? Is it possible? Will it be go out if it's if I'm only cutting using a knife for 1.5 meter, or I need to cut for the full 3 meter. Once again, it's a cake, and I want to remove this particular portion out. How to remove it? I need to cut the full 3 meter, right? I need to cut the full 3 meter. Okay. So when I say cut area here, when I say the cut area, yeah, full. Otherwise, it will not go out. It will not go out. Okay. So 3 meter. That's the first thing when it comes to. That's the first thing. So rather than saying BD, let's call it to be cut area, and you will understand in two-way shear why I didn't use BD. Okay, so 3 into. Now, if I see in a section, if this one now is point how much? 0.54. How much is your average? 0.48. If this is 0.48, now if my knife has only cut 0.2 of the depth, will the full portion go out, or you need to cut the full 0.48? Full 0.48. Okay. So I need to cut the full 0.48. So for me, when I say cut area, it means that these are the dimensions which are affected by the cut. So we are having 3 meter and then 0.48. Okay, it means that I'm having a knife which is having a total shear force of 533. Close your mic. Which will cut a length of 3 meter and a depth of 0.48. Are we clear? Yes. This is Zahra. Now once again, say Zahra. Now for you to understand, this is my plan for the foundation, and then this is my, let's say, not here, and this is my section. Now for me, okay. Now for me, this is 0.84. Okay, and this is the area. Okay, this is the area which will go up on set. Okay, this is the area. Because if you concentrated the mirror, I said that normally we calculate the stresses in Newton per millimeter square. Okay, so even that one will be shifted to millimeter. So 3,000, and then we have how much is the other area? 480. Okay, so once again, it depends on which unit that you please your mind. It depends on which unit you will be calculating. Okay, it depends on which. Asma, concentrate here and leave the slides. Shear stress can be calculated in any unit, and I told you that we are calculating it now in Newton per millimeter square. So now it's in millimeter. Okay. Now returning back returning back to the question of Zahra. Now, for me, Zahra, if I want to remove this particular portion, now this portion is actually at the end. Okay, this is actually at the end. So for me, I don't need to consider the 0.84. The position is 0.84, but I don't need to cut for any dimension of 0.84. Now for me, if I want to remove this particular portion, you need to cut the whole line. Okay, and this whole line is 3 meters. Okay. Second thing, now if I go and take this particular portion, if I want to uplift it, the second thing to be taken into account is the depth. Once again, if I didn't cut for the whole thing, this particular portion will not go up. Okay. Now, where you will be considering the 0.82, you will be considering it when you will be calculating for the shear forces. Okay. When you will be calculating for the shear forces, you will be considering the 0.82. But for me, I don't need to cut the 0.82. I need to cut two things. I need to cut the 3 meter, and I need to cut the 0.48, which is the depth. And once again, if you imagine it as a cake, you directly cut the 3 meters, and you will cut for a depth of 0.48. There is no 0.84 and 0.82 in the cutting process. Okay. You need to cut at the position of 0.82 too, but you will not cut 0.82. Okay. So how much is this? How much is this value now? The shear stress. Asma, how much is it? So we have it as 0.37 Newton per millimeter square. And once again, that's up to you if you want to use kilonewton per meter square, kilonewton per millimeter square, Newton per meter square, Newton per millimeter square. It's up to you as long as all the other checks are going to be the same. Okay, but normally we use for the stresses, we use Newton per millimeter square or megapascal. Okay, now going for the case of two-way. Now what we have said, we need to keep 1.5D, and then 1.5D, and then 1.5D, and then 1.5D. So we are going to have some kind of this shape. This particular portion will go down. And then this particular portion will go up. Yes, Bushra, you can move on. Okay. So the column will try to push down. The other portion will try to go up. Okay. So for me, I need to calculate the area. Which will go up. Okay. So once again, there is an area because of the push of the column will go down, and there is an area which will try to go up. If you remember the example of the pen and the paper. Okay. So what we need to do now, first we need to calculate how much is this particular portion. Can you help me with that? Now, if you see, we have a column here, and then we said we have 1.5D, we have 1.5D, we have 1.5D, and then we have 1.5D. Okay. So now if I want to calculate this area, if I want to calculate this area, this is 3D, this is 1.5D, this is 1.5D, and this is the column. So I can say that this particular dimension now is 3D plus the column in that direction. Do you agree? Do you agree? Okay. The other side is the same because it's a square. So we have 3D plus C. Now your 3D plus C is equal to how much? 3D plus C, where D is 0.48. The total 3D plus C is how much? C is the column. Yes, this is the column. Calculated this. So it's going to be 1.84. Okay, it's going to be 1.84. So 1.84 meter is the side of this particular square. Do you agree that 1.84 is the side of the square? Okay. Now, can you tell me what is the force required for me to uplift this portion? To uplift, let's say not to use the red color. To uplift this particular portion in green, what is the force required? Because here it's 1.5D, here it's 1.5D, and then here it's a column. 1.5D, is it from the face of the column or the center of the column? Face. So 1.5 for the first face, 1.5 for the second face. That's 3D. Plus you need to take the column into account, so that's 3D plus C. Okay. Now after we have finished, we need to calculate the force. Okay, we said we need to calculate the force. We need to calculate the force. Now, the equation of the force that we are using, total force, is equal to pressure multiplied by affected area, or affected area. Now, the pressure is how much? The pressure is 216.67. 216.67 multiplied by affected area. My affected area is 3 square minus 1.84 square. Okay, so 216. For me, I want the one in green. So it's 3 into 3. That's the outside square minus the inside square. Outside square is 3 square. The inner square is 1.84 square. So how much is this one? How much is your total force? The total force is 1216.47, let's say. 47 unit. The unit is in kilonewton. Okay. Now after we calculated the total force, we need to go and calculate the cut area. Can you tell me now what you need to cut? What do you need to cut? Once again, assume that you are having the knife. Okay, assume that you are having the knife. What do you need to cut? First thing, let us agree. Do we need to cut for the full depth? I mean, do we need to cut for the effective depth for 0.48? To remove that particular portion, do we need to cut for 0.48 for the depth of 0.48? Or you need to cut only a little bit and then it will go down? We need to cut for the whole depth. If I have, once again, if this is my foundation, and this is a column. Now, what you are telling me, you are trying to tell me that you need to cut this portion. You need to cut this portion. Now, if you see how many lines I had to do in order to draw, you will see that the first thing I tried to cut this line. Now, do I need to go for the full depth? Do I need to go for the full depth to cut it down, or no need? To remove it, do I need to cut the full depth? Are you able to remove the cake without cutting the full depth? You cannot. So you need to have the full depth. Okay. So the first thing, I need to go and put the knife for the full depth, cutting this particular length. And then after that, I'll go for the second side, and once again for the full depth. And then once again the third side and the full depth. And then fourth side and the full depth. Now at that time, you will see that these two squares are separated. Do you agree? These two can be separated now. Okay. So what is the cut area? What is the cut area for me? The cut area that we need to first agree that we are going to cut the full depth. Okay, we need to cut the full depth. The other things to be taken into account. This is length number 1. This is length number 2 that we need to cut. This is length number 3 that we need to cut. Length number 4 we need to cut. So I can say that this is L1 plus L2 plus L3 plus L4. Can I say like that? You cannot have 3 dimensions. Okay, so 4, L1, L2, L3, and L4. Can I call this one to be perimeter or circumference? Can I say the perimeter or circumference or it? You can, right? Okay, can I say that the cut area in this two-way, we have it as B into D, where B is the perimeter. And once again, because it's square, we can multiply by 4. Okay. Because it's a square, you can multiply by 4. If it's not square, you need to have the long multiplied by 2 and then the short multiplied by 2. Okay. So perimeter multiplied by D. What's your perimeter? Your perimeter in this scenario, is 4 times of 1840. So 4 times of 1840 okay, multiplied by D, and our D is 480. So can you give me this cut area? Can you give me this cut area? Can you give me the cut area? Okay, so that's 2841. Oh, can you confirm the answer for me? I mean, why are you getting it to be different answers? Okay, so it's 3. Okay. Okay, so 3532800. The cut area is a one here. Suleiman. This is the cut area. This is the area that you are trying to cut. So this is the area that you are trying to. If we go and calculate our stress for two-way shear is equal to shear force divided by cut area, and this is going to give you 1216.47 multiplied by 10 to the power of 3 divided by 3532800. And how much is the value? Suleiman, is it clear? The cut area is the one with the 1.5D. How much is the value now? The value that you are getting is 0.344 Newton per millimeter square. So we have got V for two-way, shear stress for two-way, and then we have got shear stress for one-way. So we have 0.37, and then we have 0.33, 0.344. Now the last thing that we need to calculate, if you remember, we said we need to compare between concrete. Okay, we need to which small square? Which small square in the column? Because the code says for you that you need to the affected area is going to happen after a distance of 1.5d from the face. Okay. So once again, in case of a two-way, the code says for you that you need to keep a distance of 1.5d. Okay, 1.5d. So for me, I need to cut in this position, I need to cut in this position, I need to cut in the other position if I rotate the foundation. Okay, so there is no way for you. No, it's not the same. Cut area is the one to be affected by the force directly. The force cutting the cut area. If you see, the affected area is the one which will be uplifted. Affected area, you will see that we multiplied it by the pressure. Okay, this is the one to be uplifted up. The cut area is the one to be cut by the force itself. Okay, so once again, you see the upward force is calculated by finding the area factor. After calculating this force, you need to know where to cut exactly. Okay. Now we need to calculate the shear stress. Now, since this is in the PowerPoint, I'll not go and spend a lot of time because we have already done that one. Now, if you can see, in the PowerPoint, I have tried to illustrate the equations, or the explanation is not fully there. But anyhow, shear force divided by shear area. So we have shear force pressure multiplied by area effective, as whatever we have done. So 216 multiplied by whatever we calculated. And then shear area, cut area. I think there was a mistake here. If you're having the old presentation, you just modify it. Okay, so 480. And we are going to get shear area here. Shear area is the same as saying cut area. Okay? The area that you are going to cut is the same as your shear area. So 3000 into 480, we have got it to be 0.37. And for two-way, we are going to cut the same thing. Okay. So once again, shear force, pressure multiplied by area factor. So you will see that 1.84 for both sides, so 216.67 multiplied by 3 square minus 1.84, and we have got it to be 1,200 kilonewton. And then we have got the cut area or shear area. Shear area or cut area is per meter multiplied by D, okay, where you will be getting your shear stress for a two-way to be 0.344. Now, after finding these, we need to calculate concrete shear stress, and we calculated concrete shear stress by using the equation of VC, if you remember, in the slab. So now you are going to follow whatever you have done in the slab. The only difference is calculating the one-way and two-way shear. Now VC is 0.79 gamma L 100 multiplied by AS provided, BD average, 400 divided by D. Now you can see 0.79, 1.25. We have got the area previously when we have solved for this question. We calculated the area. Okay, so I have used 1050 or 1048. So we used the equation 1048. Now here it's 400 divided by 480. Okay, 400 divided by 480, but the code says for you. The code says for you that you cannot take something lesser than 1. That's why we have taken it to be 1. Let us check the code. This is the code. So the code says for you 400 over D should not be taken as lesser than 1. So if your D value is more than 400, use as 400. Why? Okay, they have observed that after 400, it's not going to be varying a lot. Okay, after 400, the depth is not going to vary a lot. The effect of the depth is not going to vary a lot in terms of shear. Okay, so now here, okay, so we have got 0.381, and once again the code says for you, if you remember from the slab design, the code says for you, if you are going to use a grade more than 25, then you need to modify the what you call the VC and find VC new. Did we calculate for VC new? Did we calculate for VC new, taking into account the grade of concrete in the slab, if you remember? Yes. Okay, so 0.381. So VC multiplied by FCU divided by 25 to the power of 1/3. We have got it from here. For those who are asking from where we have got this one, we have got it from the code. Once again, the code says for you that for grades greater than 25, then you need to multiply by FCU divided by 25 to the power of 1/3. Okay. Now, if you see whatever we have tried to illustrate, we found VC new to be 0.425. Okay, we have VC new 0.425. Now, if you see the concrete shear stress that we have checked from the PowerPoint is 0.425. Now you are telling me that the shear stress in a two-way condition because of the loading is equal to 0.344, which is lesser than 0.425, which is the concrete shear strength. So do you require shear reinforcement? Once again, the loading shear stress in case of a two-way is 0.344. In case of concrete shear strength is 0.425, so you don't require, it's already sufficient. So we just say that no shear. Reinforcement is required. Okay. Now going for the other one, which is for one way. Once again, the shear caused by the load in case of one way scenario is 0.37, which is lesser than 0.425. So it means that the concrete is sufficient to take the shear stress caused by the load without considering any extra shear reinforcement. So once again, no shear reinforcement is required. And by now, you should be able to design an isolated foundation that is concentric, combined foundation analysis, the shear, one-way shear and two-way for foundation, for combined foundation is something similar. We'll try to see a two-way and one-way. You can see the comparison that we have done here. So it's safe or it is not required. And then this is the final detailing. We have white color and black color. Since it's square, we didn't have to calculate two moments. We have calculated one moment. So the reinforcement is going to go. T20 300 on both sides. Okay, so T20 300 on both sides. That's a black and white color. And then we have the starter bars. Okay, we have 4 starter bars for the colors. Okay, these can be taken as 12 as well. Okay, so doing that we have finished. The design of an isolated foundation subjected to axial loading. We have done a combined foundation as well. We learned how to draw the bending moment, the shear forces. We designed. We'll try next class. I'll try to solve for you a full combined foundation problem. And after that, maybe we're going to go for a centric problem where the column is not at the center, or because of the moment, eccentricity is happening. And then we'll see how to compute and how to solve for it. Okay. Any question that you have? If you don't have any question, then we have finished the lecture. And once again, I recommend you to go and solve more problems. Do not sit and wait for me to solve for you a lot of problems because we don't have time. Okay. So go and solve problems. If you require more problems, let me know. I'll provide you with problems so you can try. For example, if you are having a circular